So now we actually try and find out. Now we're trying to actually get to the good stuff here. So we take, so delta n is this, and we take the exponential of both sides, and this is the part I think we got to, except for that square root that we were.
Figure that out.
Okay, so we're done if we can show that the limit as it approaches infinity of this is the square root of 2 pi, because that's what the approximation is. So we will appeal to Wallace's formula. Taking the square root of both sides, and see, this is the cool part. This only goes up to 2n minus 1, and then notice the next odd term always starts after the even one. So you're going to end up with, all these things are going to cancel, and you only get one of them, except for that last 2n plus 1. That's where that square root comes from. Taking the square root of the whole series. Okay. So square root function is continuous, so you can interchange the root and the limit. But we'll only root 2n because 2n plus 1 is unmatched in the denominator integration. Okay, so we have this is equal to, so you factor out your 2's here. So you have this, which is n factorial, right? So you have your 2 to the n, your n factorial, then you have 1's in the numerator, and then you have the odds in the denominator times 1 over root 2n plus 1. So if we take what's in the parentheses right here and look at that, if you insert the even numbers again up to 2n, is that right?
Yes,
you get, so now you have 2n factorial.
See, we're multiplying by a bunch of ones. 2 over 3, 4 over 4, 6 over 6.
So then if you factored out the 2 again, you know, you'd end up with n factorial again, right? Just like we did right here. So if we combine it, let's see, we have the 2 to the n factorial. What's in the parentheses became this. And then you have the 1 over root 2n plus 1. So the square root of pi over 2 is the limit as n approaches infinity of all of this mashed up together. And since the limit as n approaches infinity of 1 over root 10, which is 1 over root 2n, we can write this without the root 2n plus 1 just transfer. Okay? So now, from this, we consider n factorial is this. So you use this approximation or this formula. That's exactly yes.
Right.
Yes, because the delta n is the error term. So we use that for n factorial in this limit. So another algebraic. So n factorial is that. Square root of pi over 2, that are our limits. The 2 to the n's n factorials. So if you put that in, you see all this 2 to the n, the 2 to the n, the square root of n. That's all going to cancel when you write it out. A lot of stuff cancels. So even the delta n squared is e to the 2 delta n, isn't it? So that's the same thing as that. So you just end up with this, which is right here. So that's equal to lambda squared over 2 times lambda.
Burke doesn't make that point. He calls it S sub n over S sub 2. S sub n squared over S sub 2.
Right, they approach the same
Right.
limit, yeah. So you have lambda is 2 times the square root of pi over 2, because that, the lambda squared over lambda is lambda over 2. So if you're solving for lambda in this equation, you get root 2 pi. This comes 0.
Well, that's why you wanted to define what the constant was and took Sterling a while to do it. Oh, there you go.
That's pretty impressive. That's really awesome.
No, I just cobbled together a couple things. And, you know, Brooks argued,